Okay, now I'm going to start to talk about the moment of force in three-dimensional domain. We talked about the two-dimensional domain, and it says the two-dimensional domain is used as a scalar value of force times the normal distance, so Fd, and that's the magnitude we have, and then we, based on the rotation direction, we add them together. So we have all the one, for example, rotate counterclockwise positive, all the one on clockwise negative, and then add them together as a scalar. When we're dealing with the three-dimensional force and moment, then it's easier to do the calculation in Cartesian method rather than the scalar one. If we have a three-dimensional force, and so I have a, for example, I have a point O, and I have a force F. So in a three-dimensional domain, if I want to find the moment of force about point O, this moment is, first of all, is the vector this time, because in 3D we are not doing it as a scalar. In 2D we did it in a scalar, in 3D we do it as a vector. And if I have a position vector goes from the point A connected to that force, and call it R, it's going to be the position vector R cross product of F. So that's how we calculate the moment in a 3D domain. And similar to what we have for the cross product, the direction of that moment, if we put our fingers in the direction of the first moment, and then curl it toward the first vector and curl it toward the second vector, our thumbs are going to give us the direction of that one. So again, if we have it, for example, here, if I assume that I have both of, for example, R and F sitting here, I'm drawing a little bit small. So if I have, for example, here, this is the R, and assume both of R and F are in this board plane, and this is the F. And if I want to draw to see which direction is going, so I'm gonna just slide the R a little bit here, just to make sure that both of them start here from the same point. So R, I put my forefinger to the R, rotate it toward the F, and my thumb shows where the direction of the moment. So the direction of moment is toward the board. So R, F, and directions toward board. Similar that if we have R and F, both of them are sitting on the X and XY plane, then, for example, like that, if I have R and F both are sitting on the XY and go from the R toward the F, so that's the my thumb shows the direction of the moment. So again, assume that the red one is the R and the black one is the F, and both of them are sitting on the X and Y. So if I go from the R and curl it toward the F, from the R curl it toward the F, so my thumb shows the direction of the force, which is going to be the Z upward. If it's, that's the direction of how we find the direction of force. One other point that is I need to mention is that is we need to have that position vector. It goes from the point O to any point on the line of action of the force. So again, if I have the force, I want to draw, so if I have a force like that, O, and this is the F, my first or my personal first choice is that, and that's the R. So I'm gonna put it and call it R1. So just connect it to the force. But if I extend the line of action for the force and draw the R from point O to any point on that line of action, so I assume this is going to be, for example, I'll draw here R2, I draw one here, R3, we can use any of them and this is going to be the same. So the moment about is, I can use the first one, R1 cross F, and it's equal to if I use the R2 cross F, and it's going to be the similar if I use the R3 cross F. So it doesn't matter where R goes as long as it starts from the point and end on the line of action of the force, that's okay. But majority of time we go from the point of action directly to the force. But if there's a case that it goes to any other location on the line of action of the force, like that, is still okay. So we can use it as that's okay as well. How we calculate the magnitude of the vector of the moment? As I said, if I have the vector f, again, let's draw that. So if I have a point O, force F, and the vector R. So if the R is Rx, Ry, and Rz, and if the vector F is Fx, Fy, and Fz, then the moment about point O is R cross F, which can be defined by the determinant because it's a cross product. So it's going to be I, J, K, and the Rx, Ry, Rz, and then it's going to be Fx, Fy, and Fz. And if I calculate that cross product, remember we can't do that, so it's going to be M is R cross F, so it's going to be I, and then we remove the row and the column that I is in that row and column, and write whatever left. So it's going to be Ry, Rz, Fy, Fz, then minus J. So we write the J and then we cross out the row and the vector that J is into those row and vector. So these two, and put whatever remains. So it's going to be Rx, Rz, Fx, Fz, and then plus K. So we write the K and cross out the first row because the K is in the row that the K is in, and the column the K is there. So we cross these first row and the last column and write whatever remains, which is going to be Rx, Ry, Fx, Fy. And if you look at that, again, don't forget that it's going to be positive, negative, and you have more terms, again, the same thing. So it's a positive, negative, positive, negative, positive, negative. Don't forget that the J is going to be negative. So if I expand that, so M is going to be, again, here I have a I, and then for this determinant, the 2 by 2 determinant is going to be these two times together minus these two. So these two minus these two, so it's going to be Ry, Fz, Ry, Fz minus Rz, Fy, Rz, Fy, and times I. Minus, so don't go minus, so Rx, Fz, Rx, Fz, Fz minus Rz, Fx, J plus Rx, Fy, Rx, Fy minus Ry, Fx, K. So if you look at them, these are the moment force F about point O, and if you look at here, this is the I component, so it's basically the moment about O about the X axis. this is the moment about O, about the y-axis, and this is the moment about O about the z-axis. That we can use it. So if you have the if you want to find the moment about any given point in a 3D dimension, we have to find the position vector and find the force vector, both of them as vector. Then we calculate the cross product of that, and we get that moment vector. Again, is this unlike the 2D, we did in 2D everything a scalar. We don't do anything in vector in 2D. In 3D, it's much easier to do the calculation as a vector and in Cartesian format. So in 2D, we do everything in a scalar. In 3D, we do almost everything in vector format. Okay, assume we have this shape here, this L shape here sitting here, and then we have the force F apply on that end, and we want to find the moment of force F apply on this element about point O. So want to find the moment of F about point O in this three-dimension format. To do that, first of all, we need, as I remember, so we know that the M about point O is the position vector times the cross product F vector. This is what we wanted. So if we want to find the M, we have to find R and F as a vector, and then find the cross product of them. To find the R and F, first of all, we need to go ahead and find, and this is point B, find the location of O, A, and B. So I'm gonna write them here. So the position of the O is 0, 0, 0. The position for point A is the X is 0, Y is 1, and the Z is 3. So it's a 0 and it's 1, and the Z is 3. And the position for B, the X is 2, the Y is 6, and the Z is 0. So it's 6 is 2, 6, and 0. So these are the position of O, A, and B. If I look at here, the very first thing I want is the position R, and if I look at here, what I want to get is this is going to be my R. So it's going to be R from O going toward A. So the position vector is R going O to the A, and we know that the R OA is XA minus XO I plus YA minus YO J plus ZA minus ZO K. So if I put them there, so ROA is here for the, so for O all of them are 0, so it's are 0. So from XA minus so it's going to 0 minus 0, so it's going to be 0I plus, so again here 1 minus 0 is going to be 1J, and 3 minus 0 is going to be 3K. So this is the vector that I have for OA. So that is my position vector, so I find it. Now I need to find the force F as a vector, and I only have the magnitude of that force. We remember that for any vector, we know that the vector is the magnitude times the unit vector, and here the unit vector along the force F is the unit vector AB. To find the unit vector of AB, you know that the unit vector AB is the position vector goes from A to B divided by the magnitude of the position vector goes from A to B. So to find the force F, we need to find the UAB, the unit vector along the AB. And to find the unit vector along the line of action of the force, we need to find the position vector along the AB. So we need to find the RAB. So RAB is XB minus XAI plus YB minus YAJ plus ZB minus ZAK. And if here we substitute the value for that, so B minus A, so it's going to be 2I, and 6 minus 1 is going to be 5J, and 0 minus 3 is a negative 3K. So if I write it, it's going to be more RAB. And then the UAB is RAB divided by its magnitude. It's going to be 2I plus 5J minus 3K, and its magnitude is just it's going to be 2 squared plus 5 squared plus negative 3 squared, the square root of that. So if I do that calculation, I'm going to get UAB would be 0.324I plus 0.811J minus 0.486K. So that's the UAB. And then I have the UAB. If I substitute it here, I'm going to get the F. So F is its magnitude times its unit vector along AB, which is going to be, its magnitude is 100, and times this 0.324I plus 811J minus 0.486K. So it's going to be the F. So eventually the F is going to be 32.4I plus 81.1J minus 48.6K. So now if you look at here, we have the R value, the position vector here, and we have the force here, and then so we can put them in this equation to find the moment about point O. So I'm gonna write the force F again here to have it on the board. So also the F is gonna be 32.4I plus 81.1J minus 48.16K. So it's the R, and this is the F. So that's R and that's the F. And then we can substitute it in this equation to find the moment about point. I'm going to write it here. So M is R cross F, and we know that it's going to be, if I want to write that, it's going to be I, J, K, R, X, R, Y, R, Z, and F, X, F, Y, F, Z. So it's going to be again, so I, J, and K is going to be there. So Rx, Ry, and Rz is going to be 0, 1, and 3. And here is going to be 32.4, 81.1, and negative 48.6. And if I calculate this determinant, so M about O is going to be eventually what we get is negative 291.9 I plus 97.2 J minus 32.4 K. So that's how we, so it's a Newton meter. So it's a moment from about point A. I said, so the moment is the cross product of R and F, and the cross product of R and F is, we can find it from the determinant. So the determinant is IJK, and the component of R and the component of F. So the IJK, the component of R is 0, 1, 3. So the 0, 1, 3, and the component of F is 32.4, 81.1, and negative 48.6. And if you calculate this determinant, this is what we are going to get eventually for the moment about the point O. This is our moment in the 3D domain.